All right, let's start. Good morning. Morning. Thank you.
You're welcome.
I'm going to take attendance today.
Good day, everyone.
Thank you.
You're welcome.
So we have a couple more items about matrix multiplication. In the next problem set that is due this Friday, you're going to need to use this idea of inverting a matrix when it's possible and so on. So we need to discuss that. A couple more things that I want to describe at the very least. Are there any questions before we get started? Now, to recap, I told you, think about matrix algebra in 3 different layers or steps and in increasing complexity. First layer is you just take m by n matrices. Right, so I told you that you can think of the space of all m by n matrices with real entries as a vector space in and of itself. As long as the rows and columns match, you can add and multiply. Vector space of all m by n's. Then second layer is this transpose operation. Doesn't do anything with the contents of the entries of the matrices, but somehow shapes the matrix to be of different dimensions. In particular, what it does is if you take an m by n and apply the transpose, now you have an n by m. So transpose, perhaps we can write like this. Okay. And if you want, maybe like this, something like this, transpose. Third layer is matrix multiplication. This is the more complicated part. It's still nice because for most things, you can just pretend that matrix multiplication is nothing but number multiplication. The only thing that you have to keep in mind is that A times B in general is not the same thing as B times A. Okay, and based on this, we had this bracket even. It's a certain operation. It is so important that A times B is not the same thing as B times A that people call it something. It's an operator. Okay, so commutator. It's an important thing, important aspect of matrix algebra. Now, I want to define a couple more things within this world of matrix multiplication. This third layer. These are just special case of matrix multiplication, but still. Another thing that is going to be important for us is how these 3 layers interact with each other. So, for instance, how does step 2 interact with step 1? Well, I hope you would agree in a very nice manner. Because, for instance, if I were to take A plus B, 2 matrices of the same dimension, and take the transpose, this should be the same thing as A transpose plus B transpose. Right. And likewise with scalar multiplication. And indeed, to say all this, you can just say that taking the transpose of a matrix is a linear transformation. It distributes over linear combinations of m by n matrices. I'm not going to write that down. So somehow, again, transpose work really well with vector addition and scalar multiplication. You have to be a little careful about how it works with matrix multiplication. So let's write it. Transpose is a linear op. So A plus B transpose is the same thing as A transpose plus B transpose, and a scalar multiple of a matrix transpose is the same thing as the transpose scalar multiplied. Okay. When it comes to matrix-matrix multiplication, in other words, if I'm trying to relate the transpose of the product to the product of the transposes, you have to flip the order. So AB transpose is not going to be A transpose times B transpose. It's going to be B transpose times A transpose. Okay. And one way to remember this is that in general, A transpose times B transpose is not even going to make sense. Okay. So how to think of this? Let's say A times B is well defined. Again, I'm going to give a couple examples in a second. But we had this matrix-matrix multiplication. And the rule was, well, we're writing the number of rows of a matrix here on the bottom left corner of the matrix. And here we write the number of columns. This product is well defined insofar as the number of columns of this matches with the number of rows of this. So M by N by P. Okay. In which case this product matrix is going to be of dimensions M by P. Okay. So let me write it. AB is not defined if number of columns of A is not equal to the number of rows of B. Okay? Because in terms of transformations too, we could imagine this matrix multiplication to correspond to this. First, here now I'm applying B, takes p-dimensional vectors, turns them into n-dimensional vectors, and then I apply A in composite, which ultimately gives me m-dimensional vectors. And so this is AB. Okay. So the middle term has to match in order for AB to be well defined. But then, for instance, if I were to look at, I'll use a different color here. If I were to look at A transpose, if A is M by N, A transpose is N by M. And if B is N by P, then B transpose is P by N. You see, in general, M doesn't need to be the same thing as P, which means that A transpose times B transpose in general is not defined. Okay, that's how we can remember when you're distributing transpose over matrix-matrix multiplication, you have to flip the order. Okay? And if you still don't believe me, you can just open up the definition and write down and realize the equality. Okay. Any comments or questions about any of this? Yeah?
Can you give us an example?
Example of what?
Like an example problem?
For what?
Like how that wouldn't work.
Okay. Yes. That, in fact, corresponds to this in a sense. So for instance, example. Well, here's the thing. Matrices, rectangular matrices in general, I can think of them as perhaps more general vectors. And vectors are sort of specific column matrices. Well, if that is the case, then all matrix-matrix multiplication rules should apply to vector multiplication as well. You see, this is not the same thing as scalar multiplication. Saying vector-vector multiplication. So for instance, I can think of something like this. Let's say we're in 3D, That is to say, we're looking at R3. Say V is 102, and W is minus 1, 1, 5. Okay. So these are 3 by 1s. Okay. The same dimension count is going to work even for vectors like so. 3 by 1, 3 by 1. So for instance, if I were to think of these as matrices, what I can do is, well, I can just write down V times W. But what I can do is, I can take the transpose of this and multiply it by this. Okay? V transpose W. Why? Because since V is 3 by 1, V transpose is 1 by 3. Okay? So maybe I can write it like this. The same matching business has to hold. Okay? So now, because V is 3 by 1, V transpose is 1 by 3, and W is 3 by 1. So this is now well defined. Okay? And when I do this multiplication, it's going to give me a 1 by 1. In other words, it's going to give me a number. Let's write it. Okay. In the product, I have one entry, and how am I going to get this? Well, I have, remember, the left one I split into rows, but in this case, there's only one row. There's nothing much to do. And the right matrix, I always split into columns. Again, there's only one column, and I take a row against a column, and I just zipper them up. So this by this, plus this by this, plus this by this. And that's the rule. Times minus 1 plus 0 times 1 plus 2 times 5. That gives me minus 1. This gives me 10. That's 9. Yeah?
So we have to transpose V because in order to multiply, the middle dimensions have to be.
Exactly.
So we can get rid of it.
Yes. If the middle dimensions don't match, the multiplication is not defined for us. Yeah. Does that make sense? Does this make sense so far? Okay. You see, this is vector-vector multiplication in a sense. But if I were to look at V transpose transpose, W transpose. Okay, I'm just trying to give an example as to how A, B transpose in general is not the same thing as A transpose times B transpose here. Maybe I should write that too. Okay, you cannot just distribute it like this. You always have to flip the orders of these. So this is the correct formula. What I was trying to say is that this may not even be possible. In this case, it is possible, but it's not going to give you the right value, I hope. So double transpose is the same thing as not doing anything, because if I flip once and then flip again, I get back the same thing. So this is the same thing as V times W transpose. So you see, in this case, it is well defined. So V is 3 by 1. W transpose is 1 by 3. But an interesting thing is happening here. You see, now I'm going to get to 3 by 3, in fact. Right? Because when I write this, the rule is always, when you're multiplying two things, the middle dimension is going to drop, and you're going to end up with a matrix with the sort of first dimension and the last dimension. So in this case, it's going to be a 3 by 3. Let's write it. 1, 0, 2 times the transpose of this. Now, you might see something like this. Oh, here's a column, here's a row. It doesn't matter what these are. whenever you see something on the left, you're always splitting this into rows. Now the rows here are 1 by 1. Okay. And here again, just because on the right you see a row doesn't mean that you're going to use a row. Again, if something is on the right, you have to use the columns. But for instance, in this case, this multiplication is going to be rather straightforward to do because you only have one thing or two things to multiply and no addition. I'll just do it here. Allocate your memory. Okay. For the 1, 1 entry, I need to choose the first row and the first column. So that's -1. Okay. Okay. The second row is going to be 0. The third row is going to be twice this. Okay. Any comments about this? Just to finish this up, perhaps, what we can say is, well, instead of first taking the transposes of these two and then looking at the product, we can take the transpose of this, right? That was the whole point of this example in a sense. Well, this is nothing but a 1 by 1. If you take the transpose of a 1 by 1, you're going to end up with a 1 by 1. So in this case, forget about the entries matching, not even the dimensions match. Okay, if you want. Does this kind of answer the question?
Especially because like it makes sense that that formula, the blue formula,
Yeah.
it would be like A transpose times B transpose, which is not possible.
Exactly, in general, yeah. So in this case, it was possible, for instance. But it's because the dimensions were, compatible. But even if it is syntactically possible to look at this, it's probably going to give you very different stuff.
But both of them can't be like one transpose, right?
What do you mean?
Because you have right there V transpose transpose W transpose, which is equal to V of W transpose, but both of them cannot be transposed at the same time. Right?
Oh, they could be, depending on where you start.
Unless they're the same dimension.
Yeah. So this taking the transpose of a vector to turn it into a row vector and then multiplying it against another vector ends up being a very important idea. This is what is called the dot product or the inner product. Okay. And there's a perhaps slightly more complicated version of this, which is this outer product. I want to define these. I'll do it here. So inner product or dot product. Maybe you've seen this in calculus. There's also cross product, but that's a different thing. We're not doing the cross product, for now at least. If I have two vectors, okay, in the same space and dimensions, then this dot product or inner product, V dot W, is V transpose W. Okay. So what I computed here was a dot product. It gave you a number. Later on, we're going to relate this number to the angle between these two vectors. Yeah.
Will the dot product always give you one constant?
Exactly. It's always a number. Dot product always gives you a number. eventually we're going to interpret it as angle between these two vectors. So I'll write it explicitly as well. So if I have v1, v2, dot, 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 vn, and if I'm dotting it against w1, w2, dot, 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 wn, this dot is nothing but taking the transpose of this and matrix multiplying, in which case all you're going to get is the product of the corresponding entries all added up. Okay, and like your colleague suggested, this is always going to be a number. Always a number. Always a scalar. Okay, yeah.
So if these were like 3 by 2 matrices, and we wanted to do this operation to them, would we still call that a dot product, or would it?
You can call it a dot product. That would be what is called the Frobenius dot product. Yes.
And it's not, it doesn't end up being just a number, right?
You would take something. You would take the trace of the matrix.
Okay.
Yes. Yeah. So you can do something like this with matrices as well that end up being very useful. For now, don't worry about that. When people are talking about dot product, you should just think about this. Okay. Yeah. Because somehow we're going to perhaps see that later as well. One interpretation of this number that you end up getting is it says something about how these two collections of data correlate. So you say, oh, if this dot product is 0, they're sort of orthogonal. They're independent collections of data. And when you're starting to talk about these kind of things, you also want to think about the correlation between arbitrary matrices of same dimension. Yeah. Yeah, so imagine it's like you have 2 users, let's say Netflix accounts. You sort of come up with a matrix. In the columns, you have different shows. In the rows, you have like something like that. And so 2 people are represented by large rectangular matrices. You would like to say, oh, how similar are these 2 people? Because in principle, they haven't watched the same shows. Maybe they watched, I don't know, Mad Men. They both watched it. And then person A watched Community. And then person B didn't watch Community, but watched something. Seinfeld, okay? And so you want to determine, based on something like this, if you should be suggesting Seinfeld to the person who watched Community, based on the information that they both watched Mad Men and perhaps they both liked it. So it does end up being important to be able to dot product matrices eventually, but for now, let's not worry about it. Okay? This is the inner product or dot product. Outer product is more complicated in a sense, and it's perhaps less popular. Another name for this is tensor product or Kronecker product. It has a bunch of names. I'm not going to write them. Here, I'm going to take one vector in Rn, another vector in Rm. Then instead of taking the transpose of the left vector, you take the transpose of the right vector. So VW transpose. So that now this is well defined. Right, so V is n by 1, W is m by 1, which means that its transpose is 1 by m. So the end result is going to be n by m. That's the outer product. Very nice exercise is that any outer product like this has R number 1, actually, or 0, possibly. If A is of the form BW transpose, then our number rank is at most 1. Could be 0, but at most it is 1. It's a nice exercise. Maybe doing this in general is somewhat hard to do, but you certainly should be able to just take two matrices, two vectors like this. This is the outer product, for instance. The outer product is this, and I'm telling you that this has R number 1, purely based on the idea that I know that it comes from an outer product of two vectors. Okay. Right. So you're not going to get anything here. This is like twice this. Yeah. So there's only one pivot. Maybe I should do that. So what was the rank or R number of a matrix? Well, you row reduce it to get the echelon form. You look at the number of ones, number of pivots. So for instance, example, if V is 102 and W is -115, then BW transpose is this matrix I computed over there, and 0, -2, 2, 10. Row reducing, I'm not even going to write down the operations. I take this, multiply it by 2, and add it to this to get rid of the third row. Just going to write it like so. And then if I want, I can just multiply the first row by -1 to get the reduced echelon form. Okay. Let's remind ourselves, we had this staircase. Okay. So this is of the form 1, star, star, and all zeros otherwise. We have 1 pivot, our number is 1. Okay, that's what I mean. This is true no matter which two vectors you take. Once you take the outer product of two things, that's going to have our number at most 1. Okay? Yeah.
What is the outer product? So you said dot product is similar to like.
That's the definition. Oh, outer product, what is it?
So you said dot product is kind of like similarity.
Yes.
What's the outer product symbolically, I guess? Or is there something?
It's a projection operator. That's another exercise. Let me be careful. Sometimes it's a projection operator, but if the vectors are, okay, it's not exactly a projection operator. But eventually we're going to use it. We're going to use this idea of an outer product within the context of spectral theorem, and they're going to show up as projections. I'll just say that. Later on, special outer products will show up as projections in the spectral theorem or spectral decomposition. In spectral decomposition. So physics people like to use this notation, sort of using this dot, They put this like so. This is the so-called bracket notation. And then what they do is they take this and put it here. So this is the inner product. And then you take this, put it like so. Now this is the outer product. So somehow this shows up in the spectral decomposition, which is something related to this spectral theorem, related to spectral theorem. And already, in fact, we can guess what this is going to perhaps say, because spectral decomposition, or rather spectral theorem, I told you, is about pretending that symmetric matrices are pretty much diagonal. Diagonal means it preserves axes. So we're going to figure out those axes, and they're going to show up as outer products of certain directions later. OK. Any other comments or questions? What is perhaps more important are more general, is identity and inverse operations. I told you before that I would like to imagine matrix-matrix multiplication to be pretty much number-number multiplication. And then you sort of like think a little bit about what sort of things you do with number-number multiplication. One of them is, for instance, if you have 5, you realize, or if you multiply it by 1, you get back the same thing. And in fact, it doesn't matter in which direction you do this multiplication. So, and then you say, oh, because of this, 1, in fact, is the multiplicative identity for numbers. You want to say something similar with matrix-matrix multiplication, at least for square matrices. And that corresponds to identity. So AI equals I equals, or A equals IA. And I is going to be the identity matrix, which is the diagonal matrix with 1s on the diagonal and 0 otherwise. It just ends up being the case that if you were to take a square matrix like this and multiply it against one of these identity matrices, you get back the same thing, just by definition. Okay. But then, once you have an identity element for multiplication, you say, oh, then I can think about multiplicative inverses. Then you say, oh, what is the number that, if multiplied by 5, gives me back the identity? Well, it's, of course, 1 over 5. And that's how you define 1 over 5, in fact. And again, it doesn't matter in which order you do this multiplication. But applying this to the matrices gives you the matrix inverse. The one thing, though, instead of writing 1 over capital A, because the order of matrix-matrix multiplication matters, we're going to use A to the minus 1, just like you could write here 5 to the minus 1 to represent this number. We're going to use this notation, and we're going to be careful about where we're writing that A to the minus 1. Okay? So here's an example. Just erase this as well. I had an example that I liked in the textbook. So say A is this 3 by 3, 0, minus 3, 2, 3, 8. Compute A inverse, if it exists. Okay. Now, syntactically, it's pretty much the same as doing something like this, but it's not going to be as clear as how one might compute A inverse like this. How I imagine it is like so. The inverse of a matrix, first of all, is not going to exist if the matrix is not square, at least true inverse. Later, we're going to see something more complicated, Moore-Penrose inverse, that exists more generally. But the standard inverse, which is this -1 notation, is applicable only for square matrices. And this is 3 by 3, and it's going to be OK because of that. Only for square matrices. And it's always going to be of the same dimension as the original matrix. OK? A inverse, if it exists, it's going to be 3 by 3. Why? Because ultimately, we said, oh, one way to imagine this A is a transformation of three-dimensional space. A inverse should then be the inverse transformation. OK? So it will be 3 by 3. How I imagine this is like so. Oh, I would like to say A inverse is the unique matrix solution to a matrix equation. So ultimately, then, computing A inverse boils down to solving the following. Solve AX equals identity for X 3 by 3. We need to solve this. Okay. It just turns out to be the case that if capital X solves this equation, it simultaneously solves X times A equals I. So you don't need to sort of look at both. You can just use one of them. Now, how to visualize this and do anything about it? Well, maybe I should ask you, how could one approach this? This is now a matrix equation with matrix unknown. Yeah.
Could you split this into like certain systems of equations?
Ultimately.
On, like, the different columns?
Ultimately. So that's one way. Okay. Your colleague suggests this. OK, this looks kind of perhaps complicated. But ultimately, when I open this up, this is going to give me a system of 9 equations with 9 unknowns. One unknown for each entry. Let me be explicit a little bit about this. And so when you open this equation, this one, substitute, gives you this. Then you can open everything up. The rule is always the same. The left matrix is split into rows. And the right matrix is split into columns. And you're also given what the output should be. Okay? So for instance, this says this. First row against the first column gives me x21 plus 2 times x31, okay, is 1. Then first row against the second column, x22 plus 2x32 equals 0. And then x23 plus 2x33 equals 0. Okay, I just opened up these 3 entries. And there's 6 more. Yeah.
Wait, for the answer, which did you go across or did you go down to get the 1, 0, 0?
I went this way.
That way, okay.
Yeah, yeah. Good. So I was just focusing on the first row, but essentially you would open up the definition of every single one of these entries. Ultimately, you have 9 entries, you have 9 unknowns. You would end up with a system of 9 equations with 9 unknowns. And whatever the solution of that is, would give you the inverse. Of 9 equations with 9 unknowns. If it has a solution, it's going to turn out that it has a unique solution, and that's going to be the inverse. If not, then you don't have an inverse. Okay? At this point, we don't know how to distinguish whether or not a given square matrix has an inverse, apart from actually trying to solve the system. Okay? So this is a valid method. Perhaps the problem with this is that there's going to be a bunch of redundancies, in fact, when you open this up. Because you're going to sort of write down this system of 9 equations with 9 unknowns, put it into augmented matrix. This is going to give you 9 by 10. You're going to realize a lot of the entries are 0. It's going to require a lot of padding. It's possible to use this, but a faster way of doing the same thing turns out to be this. Okay? You say, well, I start with this and put this into augmented form. This is method 1. So this is method 1. Method 2 is to not go down this path, but turn this into an augmented matrix. Now on the right-hand side, you're going to have a 3 by 3. Okay? A bar I. Okay? This is a more complicated augmented matrix than you're used to, but it's going to work. Then what do? You do a bunch of row operations to get the echelon form. Ultimately, your aim is to get identity on the left side, and whatever you end up with on the right side is going to be your inverse. Okay? So start with this, transform it into the augmented matrix like so. This is a 3 by 3. Do row reductions until row reduction. So row reduce. To get identity on the left, something on the right. Some matrix, 3 by 3. This, whatever 3 by 3 is on the right-hand side, is going to be your inverse. Okay? I'll let you think about why this indeed computes the right matrix. For now, I think what would be best is if we went ahead and, yeah, go ahead.
When we're doing trying to get it to the
Yes.
we allowed to move the rows around?
Yes.
Translate them?
Yes, but ultimately you want to get identity on the left-hand side. You need to order everything so that you have identity here. Yeah. Or you can say, just start with this augmented matrix, turn it into a reduced echelon form. If the R number of this matrix is not 3, it doesn't have any inverse. So you have to be able to get identity on the left-hand side of this augmented matrix when you're doing method 2. Okay. I'll leave you to think about why this would work. I just want to go ahead and do this multiplication or row reduction. Also, I'm going to leave this to you to sort of finish if you have extra time. This method 1. And if you end up having no time left, we'll continue tomorrow too. So I'm just going to do this method 2. What is augmented matrix? 0, 1, 2, 1, 0, 3, 4, minus 3, 8. That's my A matrix on the left-hand side. On the right, I always put identity. 1, 0, 0, 0, 1, 0, 0, 0, 1. And what's the aim? The aim is to do a bunch of row operations so that here I see this pattern and I see something else on the right-hand side. Okay. Any suggestions as to how I can start? Standard row reduction, yeah.
Row 3 minus 4 row 2.
Yeah, so you're saying I'll just take this one and knock out this 4. Right, so this was one of the operations that is allowed. You can take any row, scalar multiply it by some number, and add it to some other row. I'm not going to write down the operation. This is sort of like a reminder. Right, so because I'm multiplying this by minus 4, now I have minus 12, and this should be minus 4. You see now the right-hand side is going to start getting fewer zeros. Right, so like so. Okay, it's fine though. On the right-hand side, I want some complications. I don't care about that. I'm trying to reduce the number of zeros here. Okay, this is week 1 row reduction. What else can we do? Well, I can take this one and get rid of this minus 3. So I'm multiplying row 1 by 3. This is gone. Now I have 6 minus 4 is 2. 3 minus 4, 1. Okay. Let's continue. I want to use this guy to get rid of these. Eventually, you see, I'm going to have to worry about this 3 over 2 because I'm going to have to scale this by 1/2. But we can just leave it as is for now and just subtract it from the first row. Oh, 1, 0. And in fact, let's do both of them together to be fast. 0, 0, 2, 3, minus 4, 1. So if I subtract the third row from the first, now I have a 0 here. Minus 2, 4, minus 1. What else can I do? Well, I'm going to multiply the third row by minus 3 over 2 and add it to this to get rid of this one. So let's do this on the side. Minus 3 over 2 is 0, 0, minus 3 over 4, bar, minus 9 over 4, 6, minus 3 over 2. So I need to add this to this. Hang on a minute. Oh, this should be minus 3. Add this to this. I have minus 9 over 4 here, 7, and then minus 3 over 2. And then I might as well just get rid of this as well by 2, minus 2, 1 over 2. And finally, I need to rearrange everything. Something. I'm out of time. We're going to talk about this more tomorrow. Thank you. All right, let's start. Good morning. So we're going to keep working on this example that we started yesterday, computing the inverse. I want to say a couple more words about why this procedure works with the augmented matrix to compute the inverse. And then we're going to be on our way. So next week is our 5th week. And on Friday next week, we're going to have our first midterm. OK? So if you look at the syllabus. Morning.
Clean the whiteboard.
Thank you.
You're welcome. Tomorrow is Wednesday, everyone.
Yeah.
Have a good day, everybody.
So on the syllabus, for week 5, I wrote as a topic computer graphics. But I also wrote that it's optional. Probably what we're going to do is we're not going to spend that much time on computer graphics, even though I'm going to say a couple words about something, which is this idea of an affine transformations. These are almost linear transformations, but these are slightly more general if you look at them in a certain way. And then we have a couple of things that I was planning to discuss the week before, but we didn't have time. So what I think I'm going to do is I'm going to postpone talking about these block matrix algebra, elementary matrices, and this matrix factorization, PLU or LU, whatever. Probably we're going to talk about these next week on Monday or Tuesday. We're going to have review on Wednesday. We still have a couple of things to discuss with these linear spaces, subspaces, and so on. So the point I'm trying to make, I guess, is that all of these are going to be included in the first midterm. But certainly, the topics I'm going to talk next week about are going to be less emphasized. OK, that's why I'm sort of like pushing them back a little bit, because these are more important, the things that I'm going to discuss today and rest of this week. What else? So I'm not going to release any new problem sets this Friday. Instead of that, you're going to see some sort of an exam guide that I'm going to prepare. Once that is prepared, which is going to be on Friday, I'm going to upload it on Canvas under the midterm 1 assignment page. Probably it's going to say things like, be comfortable with doing this, that, the other thing. And also, I'm going to single out certain problems from the previous problem sets. And so that's that. Are there any questions about any of this, the exam and stuff? Yeah.
How would you recommend we prepare for the exam?
Certainly doing the problem sets is important. Thinking about the exercises that I give in class could help, even though many of the exercises I give in class, they're a little bit more advanced compared to the exam, what I would be comfortable with giving in the exam. Another thing you can do is you can look at the material from last time I taught this class, And there's like an exam that there's the exams and stuff like that, the keys and everything. So you can perhaps test yourself, see how you're holding up. The topics are going to be pretty much the same. So.
Are those past tests in Canvas?
Yeah, no, it's on GitHub. So on the syllabus, under the under the books and resources section, there's the link. You can just click on it. Yeah. Did that answer your question? Yeah. Okay. Any other comments or questions about the exam? Yeah.
Are there any problems from the textbooks that you would recommend going over, or just?
Probably I would suggest just being able to do every single example specifically. The main thing is going to be solving systems. That's going to be the main emphasis for the first exam. Also ideas like span, linear independence, these kind of things. Yeah. Yeah, you need to be able to do specifically row reduction, okay? I'm going to try to come up with nice matrices in the exam, but I guarantee you, even from now, it's there's going to be solve this system, solve that system type of stuff, okay? Because that's the bread and butter of this course. It's we keep sort of building more and more complicated ways of talking about things, but at the end of the day, the so-called assembly code of linear algebra is solving systems of equations. Row reduction. Okay. Any other? Yeah, go ahead.
How many questions are there?
Second.
How many questions are there?
I haven't prepared the exam yet, so I don't know. You can perhaps have a look at the previous exam, the first midterm from last time I taught this course, and probably that would give you an idea. Yeah. Okay. So let's go back. The example we were looking into was this. It's a 3x3, and the question was to compute the inverse, a inverse, a to the minus 1. And what do you need to know? A to the minus 1 is always going to be of the same dimension. It has to be a square matrix, right? If your matrix is not a square matrix, in other words, if the number of rows is not equal to the number of columns, this classical inverse doesn't exist. It's not defined. There's still something called the pseudo-inverse or Moore-Penrose inverse that we might discuss later. But for now, you don't need to worry about that. So it's going to be of the same dimension, and it's going to be the unique solution to this matrix equation. A capital X, I use capital because I'm sort of trying to imagine this as a 3x3 instead of a 3x1. A capital X equals capital I, and this capital I is this identity matrix. So diagonal matrix with ones on the diagonal. Okay. And if you like it better, you can write it this way as well. This is one of the sort of mysterious parts of this inverse, mysterious things about this inverse. If A inverse solves this equation, it also solves this equation. Now remember, in general, AB is not the same thing as BA. So you should not expect XA to equal to AX. But in the case of inverse, that's OK. So method 1 was this perhaps more cumbersome method. We said, I'll just open this up. It's going to give me 9 equations with 9 unknowns, and I can go ahead and reduce it and everything. But then I said, instead of doing that, an equivalent way of doing the same thing is to look at the augmented matrix. Before, we were augmenting a column matrix here on the right-hand side. But in principle, you can do the same augmentation business with any sort of equation like this. This time, I'm augmenting a 3x3. And how do you compute using this? Well, you just do row reduction, and you're trying to get the echelon form. Specifically, you're trying to create an identity matrix, that is to say this, on the left-hand side using row operations. Okay? If you can create the identity matrix on the left-hand side, whatever is created on the right-hand side simultaneously is the inverse. If you cannot create this identity on the left-hand side, that means that the inverse doesn't exist. Okay? Row reduce. If you can get to this, okay, then this is going to be A inverse. Otherwise, if on the left-hand side you do everything you can and you end up with something that is not the identity matrix, you get something other than I, which means, if you think about it, the R number, the rank of A is less than 3, then it's not invertible. In other words, A inverse doesn't exist. Okay? These are the two cases. This is the case when the R number of A is 3. So A is full rank. This is the case when A is not full rank. In other words, R number is less than 3. Okay, and of course, if I had a 7 by 7, I wouldn't ask you to do this by hand. But again, you would look at this augmented matrix. You would try to do row reduction to get the 7 by 7 identity. In which case, full rank would be when rank is 7. If your rank is less than 7, you would have no inverse. Okay, this is the general idea. Now, I was computing this, and I tried to finish, but I think in the last step I made a mistake. I'm not going to do this again, but ultimately we did this. And then we start with this, do a bunch of row reduction, so that now on the left-hand side you have identity. In this case, we did end up with this configuration. And on the right-hand side you have this. Instead of dividing it by 2, I divided it by 4, I think, here. 3 over 2. Minus 2, 4, minus 1, 3 over 2, minus 2, 1 over 2. Okay. In the exam, you can get sort of 3 by 3 at most if there's no structure. If the matrix I'm asking you to do something about has more than 3 rows or columns, probably there's some sort of a structure that I'm hoping you're going to see so that you don't do the whole sort of row reduction. Okay. Okay, so got this, and so this is A inverse is what I'm saying. In other words, just like how we could check that our row reduction was correct, that we could solve the system, whatever, to verify, you just plug in into this equation, for instance. Just to remind ourselves, this matrix-matrix multiplication, let's do this. So I want to compute A inverse. Okay, so this matrix is A, this matrix is A inverse. 4, minus 3, 8. That's A. And then here I'm going to put A inverse, which is this guy. Minus 2, 4, minus 1, 3 over 2, minus 2, 1 over 2. I want to do this multiplication. Now, again, let's recap. When you're trying to do matrix-matrix multiplication, there's a matrix on the left, there's a matrix on the right. Okay? The matrix on the left, in this case, is A. The matrix on the right is, in this case, A inverse. You take the matrix on the left, you split it into rows. Okay? That's always what you do. Then you take the matrix on the right, you split it into columns. And then you're going to mix and match. Okay? What was the idea? If you're trying to multiply two matrices like this, the middle dimension has to match. Okay? In this case, A is 3 by 3, and A inverse 2 is 3 by 3. The inverse always is going to have the same dimension as the original. And once you do this multiplication, you're going to end up with a matrix whose dimensions are this and this. So you drop the middle dimension, and the end result is going to have 3 rows, 3 columns. That's always the rule. Okay? So, I know that I'm going to end up with a 3 by 3, so I'm just allocating my memory beforehand. What am I trying to get here? I'm trying to get the 3 by 3 identity matrix. I want this one to be 1, 1, 1, and all other entries 0. In particular, I want this entry to be 1 first. Okay? To compute this, using the product, I'm going to take the first row, and I'm going to hit it against the first column. Okay? This by this is 0. This by this is minus 2. This by this is 3. Okay? So this is 1. Okay? To compute this entry, I took the first row and I hit it against the first column. Okay. And then you keep going. To compute this entry, let's say this one perhaps. To compute this entry, I need to again take, because it's the row 1, column 2 entry, I'm going to take the first row and I'm going to hit it against the second column. This against this. Okay? 0 times 7 is 0. 1 times 4 is 4. 2 times minus 2 is 0. Minus 4. In total, it's going to be 0. Okay? Make sense? I know some of you are perhaps bored, but based on the responses I got from PSET 1, I think this class is slightly above average. So if you're feeling confused, if you're one of those who are feeling confused, maybe you can send me an email so that we can discuss things and so on. I don't usually find myself in the position of trying to slow down, but yeah. I know if you have more experience than usual, in my estimation. But anyway. So again, let's do one more perhaps. If I wanted to compute this entry perhaps, I'm not going to do all of them. If I wanted to compute this entry over here, second row, third column. So I need to take the second row and the third column. Okay? This by this is minus 3 over 2. This by this is 0. This by this is plus 3 over 2. So it's 0 in total. Okay? So that's how you verify. I'm not going to do the rest. I'll leave that to you. Verify, and also verify that A inverse A is identity also. Okay? But that's how you do it. In general, this is pretty much the fastest way of computing inverses of matrices, row reduction. There are certain situations where maybe the matrix has a certain shape, in which case you can, there are certain shortcuts. I'm not going to discuss these. These kind of things, I think, in my estimation, you sort of, it works better if you sort of figure them out yourself. In the case of 2 by 2, there's a formula that is, I think, not that hard to keep in mind. You don't have to memorize it. I remember it, the formula for 2 by 2. If you don't remember it, you can again do this row reduction business. So for instance, let's look at this. Um, 136. Three, 4, 5, 6. Okay, that's a new example. Again, let's do this row reduction and try to compute. The inverse. So compute. Okay. Augmented matrix is AI. Okay. Now I'm going to do row reduction. Either A is full rank, in this case it would be 2, or it's not. At this stage, I don't know. Just going to do row reduction. And instead of worrying about these fractions and stuff like that, I'm going to take a couple extra steps to just keep using integers here. So for instance, I can do this. Multiply the first row by 5. Multiply the second row by 3. Then subtract the second row from the first one. 0, 2, 5, minus 3, 15, 18, 0, 3. Subtract the first row from the second one, or rather 6 times it. That's 15. That's 0. If I multiply this by 6, I have 30 here. So that's minus 30, minus 18, minus 15. Like this. Then I can divide the second row by 15. Minus 1. Interchange. And then I can divide by 2. At this stage, I do need to do something about this. Okay, just to verify. Seems I made a mistake somewhere.
You minus 15 instead of adding 15. It's a negative 3, so if you're minusing negative 3 times
So here, or where's the mistake?
In that calculation.
Oh, okay.
minus 15, you need to add it.
Oh, okay. Yeah, yeah. Very good. 6. Oh, minus, I see. So 18, then 21? No? Yes? Okay. Apparently, I don't know math. Okay. So divide. Oh, then I cannot divide then. So then I can, okay. I want to postpone dividing so that I don't have fractions. This I can divide by 3. Minus 10 and then 7. Then interchange. Are you sure? I feel like there's still a mistake.
I think it's right there when you're trying to get rid of the 18. Yeah, that's not by 9. Because 9 times 5 is 45.
This is the mistake? Or
Going from there to there.
this is the mistake?
The middle one.
This, okay.
When you're trying to get rid of that 8.
Oh, because I multiplied by 6.
Yeah.
Oh my God.
So yeah, it should be like negative 45 and then I think negative 24.
Yes, okay. So multiply, let's do this slowly. This is 15. Multiply the first row by minus 9, then add it to the second row.
Yeah, so it should be negative 45 and negative.
Okay. Minus 9, 27 plus 3, so minus 24. Okay. Subtracting. Okay, you're right. 30. Okay. Every semester there is a course like there's a class like this where I just like completely forget everything. Okay. Yes, now it's fine to divide everything by 15. 1, 0, minus 3, and 2. Okay, now it works. Apologies. So now this does match with the answer given in the textbook. So the point here is that this is A inverse. Same idea again works, is the point. Why did I take a couple extra steps? Well, I didn't want to use the fractions so that I don't make any mistakes, but even integers I had issues with, as you see. In any event, so this method again works, okay? We can just take that A inverse and multiply it by this, and in fact, let's do that too, just to verify. Check. Three, 4, 5, 6 against minus 3, 2, minus 5 over 2, oh, plus 5 over 2, and then minus 3 over 2, rows, columns. Okay, I'm not going to keep doing this, but let's do this one more time. Left matrix split into rows. Right matrix split into columns. You're going to end up with a 2 by 2. You're going for identity 1, 0, 0, 1. Okay. This by this, minus 9. This by this, 10. So that's a 1. This by this is 6. Minus this by this, or plus this by this rather. minus 6, so that's 0. This by this minus 15, this by this plus 15, so that's 0. This by this is 10, this by this is minus 9, so that's 1. So this is identity. And so this is the inverse. Okay, so this works again. The formula, in fact, says this. Okay. It's going to be a 2 by 2. And how do you populate? Well, you look at the entries. Okay. The diagonal 2, you flip their positions, and then you put minuses in front of the off diagonals. So in this case, the 2 by 2 there is going to be 6, 3, flip the positions, and then the other 2 you're going to put minuses in front. But there's a 1 over some number here. You need to scale this by an appropriate number, and this is this AD minus BC business. In this case, it is this by this minus this by this. So this is 18 minus 20, so it's minus 2. It's the same thing as this, because remember, this is a scalar multiplication of a 2 by 2. How do I do this? I just distribute everything. So this is minus 3, 2, 5 over 2 minus 3 over 2. So you can get the same thing this way as well. Okay. Using this formula, if this AD minus BC is non-zero, this works. If it is 0, you don't get to divide by 0, which means that the inverse doesn't exist. So I'll write it here, formula for 2 by 2. So ABCD inverse equals 1 over AD minus BC, and then DA in the diagonal, and then minus B minus C in the off diagonal. If AD minus BC is non-zero, and doesn't exist otherwise. Okay, that's the formula. Some people find it convenient to remember this, especially if you're doing a lot of calculations with inverting 2 by 2s and stuff like that. It ends up being useful. So you're welcome to use it if you so prefer. If you don't like remembering formulas, you can just do the augmented matrix stuff. Certainly it's a lot faster once you get used to it. Okay. There are likewise formulas for inverses of 3 by 3 and so on, but it gets more complicated than this, and I don't remember those kind of things. Okay. But you can try deriving them if you want. The point is that, again, you're going to have something like this here. In the case of 3 by 3, you have 9 entries, which means that this is going to be a function of 9 things. It's going to be pluses and minuses and so on. It's a determinant, after all, which we're going to talk about later. So it becomes harder to remember. Augmented matrix method is always going to work, no matter what the dimension is. Yeah?
For the formula, does it say AD minus BC?
Yes, AD minus BC.
So if this one doesn't equal 0, does that mean it doesn't exist? Or I'm just confused. So like after you write the sentence.
Oh, the inverse is this matrix scaled by this number if AD minus BC is not equal to 0. Doesn't exist, the inverse doesn't exist. Otherwise, which means if AD minus BC is 0. So. And in the first problem set 2, this sort of expression came up, remember? So this is, we're going to call this the determinant of the matrix. And in fact, I'll just do that here. In the case of 2 by 2, determinant of A is AD minus BC. We're going to later on figure out what the definition of determinant is for any square matrix. And you're going to learn how to compute it as well. Okay. Comments, questions? Now, what I want to do really a little bit here is to perhaps talk a little bit about why this method actually works. Okay, just do it here. So, say A is n by n. Okay. For A inverse, why does the augmented matrix A bar I method work? Why is it the case, in other words, that if I take my n by n, put it into an augmented matrix like this with identity on the right-hand side, and do row reduction to get identity here, on the right-hand side, I generate A inverse? Why does the method work? Any guesses or answers? Yeah.
I mean, because of the way you do matrix multiplication, you can kind of think of it as just like you're solving a system of equations, but you just have like multiple vectors that you're tracking as you're solving the system. So you have like multiple unknowns, but each of them directly correspond to one like spot in the matrix, if you will. And so when you're solving a system of equations, they each work themselves out.
Very good. So let me unpack what your colleague is suggesting. It's all in the notation in a sense, okay? You have A n by n. When you write this equation, okay, based on how we defined matrix-matrix multiplication, and in fact, perhaps I can write this a little bit more explicit. That's my A matrix. That's my X matrix. And then I have also the identity matrix. Okay? When you open that up, you get this. Now, when we're doing this matrix-matrix multiplication, if I were to only focus on the first column, which is this E1 vector in the first in the direction of the first axis in n dimensions, if you want, well, I'm always going to choose this column from X. Yeah? And so really then I can, if I were to just focus on the first column, E1 in the output, and let's call this X1 perhaps, the first column of x. Well, this just gives me ax1 equals e1. And likewise, if I were to only focus on the second column in the output, that's e2. And that's going to come from the second column here. And so I'm going to have a times x2 equals e2, dot, dot, dot. This works for each of these columns in the output. So instead of writing it like this, you can imagine I have n vector equation, or matrix vector equation, whatever you want to call them. And how do you solve these? Ultimately, this you put into a bar e1, this a bar e2, and so on. You're going to have n augmented matrices in the sense of weak 1. And then you're going to have to solve these because you're trying to solve this equation ultimately. You're trying to find the vector x1, the vector x2, and so on. And how do you do this? Well, you do row reduction. But then, this, when you think about it, as a total matrix, it has n rows and n plus 1 columns. Okay? Which means that at most, it's going to have pivots. Our number is going to be at most n. So in the best possible case, you're going to have identity here and some vector there when you end up with when you finish your row reduction. Well, as you're trying to solve this, you're trying to get identity here. But then the exact same moves, row reduction operations, well, you can apply to each of these also. And so instead of row reducing each of these augmented or standard augmented matrices one by one, you might as well just put them together and do one row reduction to solve each of these. Okay? So this is essentially why this method works. You just take A and augment to it, not one vector, but the whole matrix. And it still works. Okay? Does this kind of make sense? Obviously, you don't need to know why it works, but I think it's a good idea to think a little bit about why things do work, because eventually you're going to start forgetting why you do this, that, the other thing. So. Okay. Another thing I want to say is this. Because somehow, this is one explanation. Another explanation is by way of thinking of A as a transformation. If I were to think of A as a transformation, then A inverse should be a transformation too that rewinds whatever A did. Right? That's the point of inverting something. Inverse transformation. Invert whatever A does. Okay? Now remember, when we were talking about how to visualize matrices as transformations, I told you that when the R number is not the maximum possible, in the case of a projection, for instance, you're losing information. Those type of transformations you wouldn't be able to invert. Okay? But if the R number is maximum possible, full rank in other words, then you have some hope. Again, looking at this, no, other way around, N1, A, N2, like this, okay? Again, I have my n by n. Remember, one interpretation of this was, well, the first column of A is where A takes E1, this matrix, this vector. E1, 2. And likewise, the second column of A is where A takes the second standard vector, 2. And so on. E2, 2. Okay? So in a sense, what we're doing is this. I'm just going to draw the two-dimensional picture. This is the E1 direction, and this is the E2 direction, let's say. Or maybe I'll just use coordinates like this. x1, x2, and A. Say this is y1 and y2. Say my horizontal is blue. Okay, and my vertical is red. The first column of A is going to be some vector in the y1, y2 space. And it's going to be also the image of the blue vector here. Say it's something like this. AE1. And then let's say the second column maybe went there. Okay? And so to rewind what A is doing, somehow you want to say something like this. A inverse should be a matrix, should be a transformation that takes this blue vector back to this one. And likewise, this back to this. And so, for instance, if I had something like this, remember this was a shear, doesn't do anything with the x-coordinate, shear is the y-coordinate. Okay, so it moves things this way. Yeah. So it's, if we had this, apply A, now it's like this, sheared. And how are you going to go back? Well, you want to shear back in the same direction, which means that A inverse should be 1 minus 2, 0, 1, for instance. So I guess what I'm trying to say is, using this intuition coming from transformations, thinking of matrices as transformations, in certain circumstances you can also guess what the inverse should be, even without calculating anything. Okay? So that ends up being a useful skill. So for instance, if I had like a rotation by 45 degrees in the clockwise direction or counterclockwise direction, its inverse should be the other way around. I'll write that too. So remember, let's say r sub pi over 4. Rotation by 45 degrees. Okay, inverse should be rotation by minus 4 over 45 degrees. If you're rotating this way, the inverse operation should be rotating the other way around by the same amount, same degree. Okay? So that's all for today. We're going to continue tomorrow. Thank you. All right, let's start. So I'm going to take attendance today. So we're going to start transitioning to this ideas about bases and subspaces. And then I think on Friday, we're going to be able to state the so-called fundamental theorem of linear algebra properly for the first time. And we're going to keep repeating the theorem with more sort of statements added to it. Yeah, let's start with the idea of a basis. Okay. Basis is nothing but a set of vectors in the same space. So they have to be of the same type. That has both properties of spanning and linear independence. So I take a bunch of vectors. Let's use the set notation. So I have a set of vectors in the same vector space. Let's say capital V. I'm going to call it a basis. Or maybe I should say unordered basis, because there's also ordered bases. Unordered basis. If they have to span everything. So span is everything, and they are linearly independent. Okay. What does this mean then? It means that you have a bunch of vectors, and using linear combinations of these, you get to go to any position whatsoever in your space. And furthermore, there is no redundancy. Okay? So these are the two sides of the same idea. The first example, of course, is what is called the standard basis of Rn. So these are the EI vectors. Or maybe I should say definition. Oh, example. Standard basis of R2, let's start like this, is, well, E1, which is 1, 0, and then E2, which is 0, 1. Okay? In 3 dimensions, of course, you have the x-axis, y-axis, and the z-axis. Again, I'm going to call the first axis E1, so 1, 0, 0. And E2 is 0, 1, 0. E3 is 0, 0, 1. This is like a minor point, but if the order in which you look at the vectors matters for you, you call that an ordered basis. I'll just say ordered basis if the order matters. If the order of the vectors in your set matters. If the order matters. Okay. Now let's verify, even though it's fairly straightforward that these are standard, these are bases indeed. Maybe I should add standard basis of Rn as well. This time I'm going to have E1, E2, all the way up to En. 1, 0, all the way up to 0. All of these are zeros. And then E2 is 0, 1, 0, and so on. And then En is 0, 0, dot, 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 0, 1. So when people ask you, is this a basis or whatever, you need to do two things, right? You need to figure out if it spans, that set spans the whole space, and you need to verify that these are linearly independent. So for instance, let's do it with the plane, with this case. We had in fact done this before. Using only these two vectors, can I get to any place in R2? Well, yes, if I were to take an xy, a general vector, right, this is x times E1 plus y times E2. So the span of E1, E2 is R2. Okay? How about linear independence? You have had some experience with this. Now what do I need to do? I need to say, oh, I'm going to take a linear combination of these two and say that linear combination is the zero vector. So C1 E1 plus C2 E2 is 0. Then this means that C1 C2 is 0, 0, which means that C1 is 0 and C2 is 0. So these are also linearly independent. So you check this and that, spanning and linear independence. If you have both, that means that you're a basis. Okay? Yes?
There one basis for each. There is one basis for each dimension, but are there other standard bases that are not related to, you know, R to the n?
When people talk about standard bases for R to the n, they mean things like this. But that is not to say that there are no other bases.
So in that case, what are we? So I can see that we're seeing that the span of that standard basis is R2, but given an arbitrary base.
Let's do another one. I can also use the diagonals, for instance. Here's another basis example. V1 is E1 plus E2. V2 is E1 minus E2 in R2. Okay? So V1 is 1, 1. V2 is 1 minus 1. Instead of looking at the horizontal and vertical axes, I'm looking at the diagonal axes. Okay? Now, I claim that this is also a basis, but it's not the standard basis. It's a different basis. Okay? Again, I need to check two things. First, I need to verify that you span everything using these two. I'll do it here. So, well, I'm going to take xy arbitrary, and I'm going to try to come up with two scalars, let's say C1 and C2, such that C1v1 plus C2v2 is this. Okay? So what does this mean? I chose xy arbitrary, and I'm asking if I can solve this equation for C1 and C2. So for xy arbitrary, can I solve this for C1 and C2? This for C1, C2. That's what it means to verify or figure out if these two vectors span everything. Okay? Now, what do you need to do? You need to just open everything up and so on. I'll erase this. So I'm just expanding everything. Xy equals, this is a scalar multiplication. I'm just going to distribute the scalar over the entries. And then I'm going to, again, have a scalar multiplication here, and then I'm going to add everything up. In total, you have this. Okay? But then if I want, I can think of this like this. 1, 1, 1 minus 1 applied to C1, C2. Matrix multiplication. Okay? So call this A, for instance. You can solve this too if you want the linear system notation, but let's practice our matrix algebra. Call this 2 by 2 A. I look at the AD minus BC, right? That determines if a 2 by 2 is invertible. AD minus BC in this case is minus 1. Minus 1 is minus 2. AD minus BC is not 0, which means that A is invertible, which means that you can send it to the other side. So that was the rule for 2 by 2. If you have a 2 by 2, there's a formula, explicit formula as well, as to the entries of A inverse. But you want to sort of go fast, you'll just look at the AD minus BC. So this by this minus this by this. If that number is 0, your matrix is not invertible. If it is 0, yes. If it is not 0, then it is invertible. So AD minus BC okay, so I'm looking at a matrix like this, ABCD. So AD is minus 1. Well, I'll be explicit. 1 times minus 1. And then minus 1 times 1. That's minus 2. Minus 1. Sorry, that's minus 1. That's also minus 1, which means this is minus 2, which is non-zero. AD minus BC non-zero means A inverse exists. Okay? So I write xy equals A C1 C2 because A inverse exists. I'm left multiplying both sides by A inverse. The A cancels out here, and I have A inverse xy. Now at this point, I can go further and open up the definition of A to actually solve the system for C1 and C2 in terms of x and y. But the point is that I know that this is some matrix, which is 2 by 2. I can multiply this, and there is some values. And in fact, there are unique values. So this has a solution. I don't need to solve explicitly. Just by the fact that this has a solution, I have that this spanning is true.
And you're asking if it's specifically if it spans R2.
Yes.
Right.
Yes. This is R2 case, yes.
Meaning if you said the same example just in R3, then you would say no, it does not span its line basis in R3.
You mean if I had like zeros here? Because these are two-dimensional vectors.
Yes. Yeah, I guess so, yes.
Yeah, so if you had zeros here so that you're now in 3 dimensions, yes, in that case, you wouldn't be able to span everything. We'll do that too in a second. So, slowing down, bases, okay? 2 conditions, span, linear independence. This was a standard basis for R2, 1001, but there are many other bases of the same space. For instance, if I add and subtract E1 and E2, I get these 2 vectors, 1, 1, 1 minus 1. Again, I need to verify 2 things to answer the question of whether or not this new set of vectors spans, or rather, is a basis of R2. I need to check 2 things. First, I need to figure out if they span everything in R2 again. Okay, this is my space in 2 dimensions. I take an arbitrary xy, and I'm trying to figure out if I can write an arbitrary xy as a linear combo of the 2 vectors I chose. This argument so far says yes. So spanning part is OK. Any comments or questions about this? We're not done, OK? Question? OK. OK. But we're not done. I need to check if these are linearly independent as well. So yes, to span. Now I check for linear independence. Now I need to set up the equation with linear combination equals 0, right? C1 V1 plus C2 V2. But then you're going to realize this thing is the same thing as this. Okay? But this is the same matrix as the matrix that we used before. Again, by the fact that this is invertible, I can send it to the other side. Whatever this 2 by 2 is, right? Like I know that it's a 2 by 2, and it's the inverse of this matrix. I don't need the entries. I know that it's a 2 by 2. It's a linear transformation. And I know that whenever I apply 0, whenever I apply a linear transformation to a 0 vector, I'm going to get 0. Which means that the only solution to this is when C1 is 0 and C2 is 0. That's what it means for V1 and V2 to be linearly independent. Linearly independent. So spans are 2 and linearly independent. And at this stage, I can conclude that indeed this new set 2 is a basis. Okay? So you take this, spans everything, also linearly independent. You need both of these conditions. Okay? So basis. It's a different basis. Okay? Any comments or questions about this? Yeah?
So does this mean that any system like this that's invertible is also linearly independent?
I guess what you're trying to say is this. If I were to take a bunch of vectors like this, I can put them in a matrix as columns. That would be a base. So that vector would be, that set of vectors would be a basis if and only if that matrix you end up with is invertible. That is true. I'll write that down. So I'll write it here. Very good. So V1, V2 dot 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 Vp in Rn is, well, this set is basis, is the same thing as saying that the rectangular matrix you obtain by considering these as columns is invertible. And what are the dimensions of these? These are all n tuples, so n rows, p columns. This already tells me, for instance, that this cannot be a basis if p is not equal to n. In Rn, if your set has less than n elements or more than n elements, it's not going to be a basis. Okay? This doesn't mean that if you have n vectors in Rn, that is always going to be a basis. Then you have to check if this guy is invertible. Because there are square matrices that are not invertible after all. So basis means n equals p. Make sense? Let's do one more example, the one that your colleague suggested. So I want to take the same example, but I want to interpret it in 3 dimensions. So I'm going to say, oh, these 2 vectors, but the third entries are 0. Or I can say, I'm going to think of E1 and E2 to be in R3. That's valid to do. In R3, again, V1 is E1 plus E2, which now is 1, 1, 0. And V2 is E1 minus E2, which is 1, minus 1, 0. Okay, and I'm looking at, again, V1, V2. And I'm asking, is this a basis? Now, based on this observation, we can immediately say no. This is 3. I have 2 of them. This is going to fail to be a basis. You can do this shortcut, or you can go ahead and check linear independence and spanning. Okay? So, method 1, 2 is less than 3, so not a basis. Method 2, you go through the 2 parts. In this case, for instance, these 2 are going to be still linearly independent, but they're not going to span everything. So I'm just going to check the span. Well, in this case, you can eyeball and realize that V1 and V2 don't allow you to move in the z direction. So if I were to, for instance, look at 0, 0, 1, you wouldn't be able to write this as a linear combo of these 2. Has no solution. So no. Okay? And in fact, if you want, you can sort of go a little bit deeper about this. In Rn, if you have fewer than n vectors, as in this case, spanning is going to break down. Okay? You will not be able to span everything. I'll write that. On the other hand, if you have more than n vectors in Rn, they're going to be definitely linearly dependent. So I've been emphasizing this dimensionality count starting from week 1. This is like very useful in general. It allows you to just like fast forward a bunch of calculations. Okay? That's why I've been sort of mentioning these. If I have p vectors in Rn, okay, so we have 3 cases. So 1, 2, 3. Then 1 of the 3 happens. Then exactly 1 of the following happens. Either 1 or 2 or 3. Either p is less than n, p is equal to n, p is greater than n. Okay? In the first case, you don't have sufficient domain vectors. This set is going to fail for sure to be spanning. Not spanning Rn, which means that not a basis. If p is more than n, then linear independence is going to fail. So they're going to be linearly dependent, which means, again, it's going to fail to be a basis. If p is equal to n, either can happen. May or may not be a basis. So this is the case where you do need to do some calculations. Okay. Let's think about an example when p equals n, but your set fails to be a basis. So for instance, in R2, well, let's do in R3. Let's say V1 is 1, well, V1 is E1, Okay. E1, E2, and E1 plus E2 in R3. So E1 is 1, 0, 0. E2 is 0, 1, 0. E3, or rather, E1 plus E2 is 1, 1, 0. At this point, you know that whenever you have a linear relation like this between your vectors, this means that this is linearly dependent. They're dependent on each other in a linear fashion, right? Which means that this is going to fail to be linearly independent. So you see, in this case, linear independence fails. And in fact, spanning also fails, as you realize. Not, well, LD, and also not spanning. This is harder to see, but in the case when p equals n, in fact, either both are going to be true or neither are going to be true. But that's harder to see. So not a basis. Okay. And of course, they might give you a more complicated vector or a bunch of vectors, in which case you're going to have to do some calculations. At the very least, you're going to have to put them in a square matrix, and you're going to do some row reduction, whatever, to figure out if the inverse exists. Later on, after the first midterm, we're going to talk about the determinant, so this AD minus BC business, but for any n by n, in which case you're going to have some sort of shortcut, even though computing determinants are also not that straightforward. It takes some time. So you're going to be able to use something like this AD minus BC condition to figure out if your basis, if your set of vectors is a basis or not. Okay. Now, I should say one thing. This is where things somewhat get complicated. And it's a very important observation. The reason why we call the standard basis is not mathematical. There's no mathematical reason. So, again, standard basis for, let's say, R3 or R2, E1, 1, 0, E2, 0, 1. So somehow, the notion of a basis is something we put on top of the vector space. It's not part of the vector space in a sense. It's about how you see it. From a physics perspective, you want to think of a basis as an inertial frame. And laws of physics should be independent of how you visualize them or how you see them. Okay? So the fact that we call this the standard basis has nothing to do with the math itself. If anything, this has something to do with evolution, human evolution. Like our eyes, like, planar things, and we like the horizontal and vertical. My biology friends tell me that, for instance, the human eye, so this is from the behind, has two sets of muscles. So these two allow you to move your eyes this way, and these two allow you to move your eyes up and down. So horizontal and vertical, sort of like, these are compatible motions with our biology in a sense. This is kind of pseudoscience, of course. I'm not a biologist, so I don't know how valid this is. But if anything, the way I sort of think about the standard basis has to do with this. Like it has to do with horizontals and verticals being sort of natural for us. It's not really about the math itself. Later on, we're going to start sort of separating the idea of a basis and from the vector space itself. We're going to start talking about this relativity. Because ultimately, we would like to be able to say, oh, if I see something and if someone else sees the same thing, well, we would like to be able to say, even though we are different people and we're looking at the same thing from different places, we're seeing the same thing somehow. So this is where we're going to start talking about change of bases and stuff like that. And then it's going to start becoming an issue, this distinction between a linear transformation and the matrix representation of it. For now, we don't really need to worry about these kind of things. Okay. So for instance, the spectral theorem really is going to say any symmetric matrix with respect to an appropriate basis is diagonal. We're going to say something like that, for instance. For now, you don't need to worry about that, though. Okay? I want to say one more thing. Perhaps let's talk about the standard basis of a space of matrices. So the standard bases of Rn are like this. You do something similar with matrices. So standard basis of 2×3s. Of the space of 2×3 matrices. Okay? Well, I'm just going to write that down and leave it to you to verify linear independence and spanning. So it's going to be like so. Then 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, like this. Okay. The 6 matrices constitute the standard basis for the space of 2×3s. Why? Because, if you were to take any 2×3, well, you can just, split the different entries, and you would write them as a linear combination of this. You can also think of it like this. To specify a 2×3, you need exactly 6 numbers. In other words, you have 6 degrees of freedom. The number of degrees of freedom is the same thing as the number of vectors you need to have in your basis. Okay, you can think of it that way too. Another way perhaps we can try to understand these is this. In fact, we can realize each of these vectors to be outer products of standard vectors of Rn's. So for instance, this I can think of as this. 1, 0 against 1, 0, 0 transpose. So this is an outer product, if you want. We had talked about this last time. Take a standard vector for R2, standard vector for R3, and I outer product them. Now it's a more complicated vector in a sense, a tensor, if you want. And you can do the same thing with the other ones. Um, 1, 0, then 0, 0, 1, and 0, 1. Okay. Perhaps that gives you a different sense of this idea of an outer product. Outer product. Okay. What is the sort of deeper point behind this? Well, 2×3s is the same thing as linear transformations from R3 to R2. And so if you have 2 vector spaces like this with their specified bases, R3 has its own standard basis, E1, E2, E3. So does R2. Well, you would like to be able to think of linear transformations between these 2 spaces for which you have bases in terms of a basis that is compatible with the bases that you've chosen. So that's sort of the idea behind the outer product, perhaps. Not that it matters for us that much. Okay? And so the exercise is to verify first, the exercise here, is to verify that these 6 2×3s indeed constitute a basis for 2×3 matrices, And second of all, to verify these matrix-matrix or vector-vector products. Okay. And I hope you would agree with me that each of these standard 2x3s has a R number 1. Each of them have rank 1. Okay. They're not in reduced echelon form in general. So for instance, this one is reduced echelon, this one is, this one isn't. The reduced echelon form of this is this. Okay, it's such is life. Okay. Comments, questions? Okay. So now we need to define this idea of a subspace. Subspace basically means span of something. Okay, that's what that means. You can also think of it as, well, it's a set of vectors that is closed under vector addition and scalar multiplication. But I think in practice, it ends up being more useful to think of it as the span of a bunch of vectors, whatever those vectors are. So definition. Subspace of V, a vector space, is the span of some set of vectors in V. Some set of vectors in V. Okay. So maybe we can think about examples. So for instance, if we're in 2 dimensions, we have a bunch of subspaces. Okay? You should expect infinitely many subspaces. Technically, I can just take the set of vectors to be only the 0 vector, in which case its span would be just a 0 vector also. So this is a silly thing to say, but 0, 0, like so, is a subspace. Then I can take span of, let's say, xy, or let's say v1, v2. But of course, I want at least one of these entries to be non-zero, because otherwise I'm in this case. Well, if I take a non-zero vector like this, and if I were to look at the span, now I get a line in the same direction as the vector. Line in the same direction as v1, v2. In the direction as v1, v2. Right? So this is just a vector, but when you look at the span of it, you get the subspace. And so, for instance, I can look at span of 2, 3. Okay, that's an example, for instance. Well, how am I going to figure out this subspace? First, visualize this vector. It's an arrow. Okay. That's your vector 2, 3. Okay. Now you use that to go to wherever you can. That's the span of that. Well, it's all the other points in the same line, right? In the line parallel to this arrow. So this is the vector. The whole line is the span. That's the span. That's the vector. Okay. And of course, I can look at different vectors like this, in which case I would have different subspaces. There are infinitely many lines passing through the origin, after all. Yeah.
How would I express this subspace? Would I just say like the subspace is 3v2 equals v1, 2v1, or?
What do you mean?
How do I express the subspace?
I would say this is a span of v1, v2. I would say this is the line that is spanned by v1, v2, because I know that this is going to be like one-dimensional. Yeah. So. Line spanned by v1, v2. Any other comments or questions? Now, technically, of course, if you were to take the set to be a basis of your thing, the whole thing is allowed. So this is, again, kind of dumb to say, but V is a subspace of itself also. So R2. R2 is span of E1, E2, for instance. Okay. So these are all possible kinds of subspaces of R2, for instance. Okay. Let's do one more, maybe in R3. I'll do it here. And in fact, let's have some fun. Let's animate this a little bit. Example. Well, let's first talk about arbitrary subspaces of R3. Again, it could be just a zero vector, or it could be the span of one vector, v non-zero. These would be just lines in 3 dimension. They could be planes passing through the origin. But just so that I guarantee that this is a plane, it's 2-dimensional, I need to have that these are linearly independent. Or it could be everything. Okay. Okay. These are all possible kinds of subspaces in 3 dimension. Okay. If your ambient space is 3-dimensional, either your subspace is going to be 0-dimensional, 1-dimensional, 2-dimensional, or it's going to be everything. Okay. Now on Friday, we're going to make more sense of this word dimension. I've been using it, in fact, since week 1. It's somewhat of an intuitive idea, but it is a rigorous definition, which you should know. Before going into that, let's do an example that is perhaps related to this. Here's another example, perhaps. We can animate this a little bit. Let's say, I'm going to think of this. So I'm going to call H sub t. This is going to depend on time. Okay, it's a subspace that depends on time. Span of 1, 0, 0. And then I'm going to lerp E2 and E3, okay? Linearly interpolate. I'll just have E1 here plus T, E3. Let's say T varies between 0 and 1. Okay, this is what is called linear interpolation. Okay, they use it in computer science and math in a bunch of different places. What is this doing? Okay, I want to think of t as time. When time is 0, okay, this scalar is 1, this scalar is 0. So when time is 0, h sub 0 is the xy plane. It's the span of E1 and E2. As I'm increasing t from 0 to 1, Well, I'm slowly sort of reducing the effect of E2 and increasing the effect of the z-axis. And in particular, when time is 1, now this is 0, and this is going to be 1. So when time is 1, this is going to be the xz plane. Does this make sense? Okay. Just to have a picture, this is x, this is y, this is z. When time is 0, h0 is the xy plane. So it's this. Okay, this is h0. And what is happening here? I have E1 here and E2. And this is E3. This lerp sort of transforms or deforms E2 to E3. Okay. At time t, you're somewhere here, for instance. Okay. So the second vector is a time-dependent vector. At time 0, it is E2. As you're increasing time from 0 to 1, it sort of turns into this. And since you're looking at the span, as your second vector moves from here to there, well, you're taking this horizontal plane and sort of you're lifting it this way. Okay? So I'm not going to draw HT because it's like slanted, imagine. But this is at time 1. Okay? This is the xz plane. Make sense? Okay. Now, two important, or maybe I should say, the most important source of a subspace really is not just a bunch of set of vectors and you take the span, but rather you start with a transformation. In other words, you start with a rectangular matrix, and to a rectangular matrix you get to associate two subspaces that are very important for us. One of them is what is called the column space. The other one is what is called the null space. So definition, say A is from Rn to Rm, so it's an m by n. Null space is perhaps slightly harder to describe, but the column space of A is rather fast to describe. It's the space that is the span of the columns of A. Okay, so column space of A is span of columns of A. Okay, that's the definition. We'll end here for today. We're going to continue on Friday. Thank you. All right, let's start. Good morning. So we have a couple of things to discuss. I want to say a couple of words about this. Your form responses for problem set 1. I was hoping to do this back on Monday this week, but I just didn't have time to sit down and sort of read. Later today, we're going to release the grades for PSET 2. And you're also going to see a guide, a document for the first midterm, which is next Friday. So I'm going to upload this guide on Canvas under the assignment page for midterm 1. You'll have access to it later. Okay, so some statistics. factoids, interesting things. In terms of math foundations, which category do you fall into? 50% approximately said somewhere between, and around 40% more comfortable. I'm guessing that's because of the majority, or that's because of the sort of electronic engineering students here. Electronic engineers are very good at math. So, yeah, like I said, it seems like this class is more advanced than usual, than expected. Ultimately, this is like a second-year class. How much experience with matrices and linear algebra would you say you already have? 70%, a little. That's again like above average as far as I'm concerned. How many STEM courses? 3+, around 70%. Regarding which day you started working on the problem set, I, generally speaking, like the distribution. Most of you basically started working on it at least on Tuesday. Yeah, like I said, it's like, even though the first couple of weeks you might sort of get away with starting the problem sets, on Friday, it is due, eventually things are going to get more complicated. So it's good to sort of build the appropriate habits. Yeah, regarding comments about specific problems, many of you said there's a lot of like busy work in these problems, which, to some extent I agree. I guess perhaps my approach is, wax on, wax off a little bit. It's like, I try to sort of modulate it, but I will try to make appropriate changes based on this. My philosophy, at least when it comes to sort of computational linear algebra, is, there's a lot of like calculations, but yeah, it's like tedious, and as a response to this, tedious amount, or as a response to this, how to say, volume of tedious calculations, you sort of start learning higher order things. That's sort of how I learned linear algebra, to be frank. It's like I would not understand the span, linear independence, whatever. I would initially just reduce everything to systems, solve it, whatever. And then eventually I started sort of realizing, oh, I can take a shortcut here and stuff. But yeah, I will try to change things accordingly. And I really liked your responses to AI stuff, for those of you who did use AI. Some of you said, AI sucks at math. That might be true now, but by the time you graduate, I feel like things are going to be somewhat different. Now, frankly speaking, I don't quite understand, I don't quite know what's going to happen when it comes to AI. Some people who seem to know what they're talking about are very scared, and some people they're concerned, and some people are, it's going to be like a sigmoid, and it's going to sort of have a horizontal asymptote. It's not that serious, whatever. But I think at this stage, sufficiently many significant people take this seriously. And so it's going to be a real challenge, I think, at least to some extent, to justify that you should be hired instead of just using AI. So I think that part in the Google form is going to help you out. What exactly you're sort of contributing to the solution of the problem, and what can be sort of automated using AI. There's a couple like personal things. I'm not going to read those out here, but I'm generally happy with the responses. Okay. And I apologize, I'm kind of under the weather today. I feel under the weather. Okay, so today I want to talk a little bit more about this column space. Then I'm going to define this nullspace. And then the three things that are very important: dimension, rank, and nullity. We've been using this idea of the rank since week 1, pretty much. Remember, rank is the same thing as R number. And by the end of today, I hope to be able to state the first version of the fundamental theorem of linear algebra. You might also see the word or phrase rank nullity theorem. In the textbook, they call this the rank theorem. Okay, so these are all the same things. It's all the same. So rank theorem, rank nullity theorem. Okay. Now, here's a definition. We had talked about columns. We had talked about subspaces. Subspaces are just spans of a bunch of vectors, or it's a space that is closed under vector addition and scalar multiplication. Subspace is the same thing as span of S for some set of vectors for some S. Or it's something that is closed under vector addition and scalar multiplication. Set closed under vector add and scalar multiply. Okay. And I told you that column space and null space are, in a sense, special cases of subspaces. But maybe we can talk a little bit about, we can give an example of a subspace of, say, 2 by 2 matrices. This is rather important. So my space is 2 by 2s. Then I can look at W, which is matrices of the form ABCD, where A plus D equals 0. Okay. So this is what is called the space of traceless 2 by 2 matrices, because this is what is called the trace. Turns out to be very important. So let's try to verify. We can either try to display this W as a span of something. Remember, in this context now, my vectors are 2 by 2s. Or we can try to realize that, indeed, if I were to take 2 traceless matrices, add them up, the end result is going to be traceless. And likewise, if I were to take a traceless matrix, scalar multiply it by some number, that end result is going to be traceless also. So W is a subspace of the space of 2 by 2s. Of 2 by 2s. Okay, and how do we verify this? Well, if I start with something like this and then add to it this guy, say this is in W and this is also in W. So A plus D equals 0 and X plus T is 0. Well, how do we add two matrices of the same dimension? Let's remind ourselves. Well, you just compare the corresponding entries and you add them up. Okay, you're going to end up with, again, a 2 by 2. A plus X, B plus Y, Z plus C plus Z, and D plus T. But of course, if A plus D is 0 and X plus T is 0, then certainly A plus X plus D plus T is also 0. So you see, if I start with a matrix, a vector in this W, and add to it another vector in the W, I get back yet another vector in W. So this guy is closed under vector addition. So vector add. Maybe I should say matrix add, but OK. And again, if I were to start with ABCD and scalar multiply it by, let's say, E, some constant, some scalar, how do I do this? Well, I just distribute the constant over all the entries. And so I end up with EA, EB, EC, ED. But again, if I started with a matrix in W, that means that A plus D is 0. But certainly then, E times A plus E times D also has to be 0. So W is also closed under scalar multiplication. Scalar multi. Okay. Now, just to reiterate, in this example, I'm thinking of 2 by 2s as vectors themselves. And so in this context, I'm not really thinking about matrix-matrix multiplying, even though it is defined. That is not about subspaces. Okay? Subspaces are all about vector add and scalar multiply. So the first layer of matrix algebra. Any comments or questions about this? OK. Well, let's also try to display W as a span of a set of matrices. That's one way of verifying that W is a subspace. Another way is to realize that W is a span of something. It's a bunch of matrices. So for instance, what I can do is well, because A plus D equals 0, that's the same thing as saying D equals minus A. And so one matrix I would use is 1, 0, 0, minus 1. Another one would be 0, 1, 0, 0. Another one would be 0, 0, 1, 0. What does this mean? This means that any 2 by 2 matrix in this W can be written as a linear combination of these 3 matrices. Okay? But furthermore, any 2 by 2 in W can be written as a unique linear combination of these. In other words, these 3 matrices are linearly independent. That means that indeed these 3 matrices constitute a basis for W. Okay? Also, they are linearly independent. Span plus linear independence means basis. Okay? And indeed, this is a useful thing to think about. If you have a subspace, and if you had a bunch of vectors in it, that set of vectors that you chose would be a basis of the subspace you have. If and only if any other vector in that subspace can be written as a unique linear combination of the vectors you chose. So I'll write it here. The set of vectors in some vector space V is a basis if and only if for any V, oh, don't know this symbol, for any V in V, there are unique scalars C1 dot 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 Cp such that V is the appropriate linear combination. Such that V equals Ci Vi. Okay. Okay. Now, the two important types of subspaces are, well, they come from transformations. They're not just a bunch of vectors in principle, but rather you have a linear transformation that you're looking at, and to that you associate two subspaces. One of them is the column space, the other one is the null space. Column space is slightly easier to visualize or understand. Null space is somewhat more sort of backwards in a sense. So if I have a linear transformation from Rn to Rm, which means, remember, that A is pretty much an M by N matrix. Then the column space of A is a certain subspace of Rm, of the output space. And the null space of A is a certain subspace of the input space. Then I think this is the notation we use in the textbook. Col of A, column space of A, well, this is nothing but the span of the columns of A. Okay. In a second, I'll do an example, maybe two actually. So this is subspace, I should write, of Rm, of the output space. Output space Rm. Okay. Right, because this kind of makes sense, because I'm saying A is m by n, which means that each column of A is going to be m-dimensional. And so when I look at the span of these m-dimensional vectors, well, it's going to be a subspace here. Because in principle, n doesn't need to be the same thing as m. Okay. That's the column space. Null space and I think the notation for this is null of A null space of A. You might also see the word kernel. I don't think we use it, so I'm not going to mention that. Okay, this is kind of confusing. But this is the solution. This is the collection of all solutions of Ax equals 0. So in a sense, null space is all vectors in the input space that A transforms to the 0 vector. Okay. Now, this is m by n, so the input space is n-dimensional. So any x here is an n-dimensional vector, which means that null space is going to be a subspace of Rn, not Rm. Okay. Before going any further, let's do an example. Um, 182. Okay. Let's start with this. I'm going to first start with a matrix that is already reduced, okay? The important thing you should keep in mind regarding column space and null space, and that is the main sort of complication here. When you do row reduction, you're going to possibly change column space and null space. Okay? You start with a matrix, start doing row reductions and stuff like that. You're going to be able to get something related to these spaces. Specifically, you're going to get their dimensions, but not necessarily how they're configured in the larger space. So because of that, let's first start with a matrix that is already in reduced form. Okay? So here's my A. Okay, 1, 0, 0, 0, 0, 1, 0, 0, minus 3, 2, 0, 0, 5, minus 1, 0, 0, 0, 0, 1, 0. Okay. So I want to understand the column space and null space of this matrix. First of all, the first thing we look at, as usual, is the number of rows and columns. This has 4 rows, 5 columns. Okay? Record it here. And so if I were to think of this as a transformation, that would go from R5 to R4. You start with a 5-dimensional vector. If you apply A to it, you get back a 4-dimensional vector. Okay? Now, what else can we say? Well, this is already in reduced echelon form. Let's draw the staircase. Remember, we want to start here, and we want to end here. And we have these listed like so. Okay? That's my staircase. This is already in reduced echelon form. Let's record it. Okay, what else can I say? What is the R number, for instance, of this matrix? What is the rank? 3. Why? Because I just look at how many steps there are, right? 1, 2, 3. 3 steps. R number is the same thing as rank, which is the same thing as pivot columns. Okay? This is a pivot column. This is a pivot column. This is a pivot column. Okay. Let's also record which columns are the pivot columns and which are the non-pivot columns. Well, first, second, and the fifth column are the pivot columns, and third and the fourth columns are the non-pivot columns. Okay, this, Okay. Here's another question. Say I give you a system of the form AX equals B for this matrix. You solve it whatever. How many free variables are you going to see when you solve it? You think one? Any other guesses? Okay. 2. Okay. The number of non-pivot columns is going to be the same thing as the number of free variables you're going to see always. Okay. Let's perhaps open this up. This is a very important idea. So the number of non-pivot columns is the same thing as the number of free variables you're going to see. So, so this is 3. Number of non-pivot columns is the same thing as the number of free variables. Okay. Now I want to convince you that this is indeed the case. So let's set up an equation with this specific matrix, AX equals B. I'm going to keep the right-hand side sort of arbitrary also. Yeah.
I thought it should be R5 to R4.
Very good. Yes. Made a mistake. Thank you. Okay. Delete this. So think about the system AX equals B. I'm keeping B to be arbitrary, okay? Now, A is 4 by 5. In order for matrix-matrix multiplication to work, lowercase x, insofar as it's a column matrix, is going to be 5 by 1. And B is going to be 4 by 1. Otherwise, matrix-matrix multiplication would not work. Okay? And so, for instance, if I were to open this whole thing up, let's say x has inputs, x has entries x1, x2, whatever, and B has entries b1, b2, whatever. What does this say? This says x1 minus 3x3 plus 5x4, and that's it, equals b1. x2 plus 2x3 minus x4 equals b2. x5 equals b3. And we don't have anything else. The last row doesn't say anything. Of course, this requires that if this A is the left-hand side matrix, in order for this system to have a solution, remember, the last entry of B has to be 0, okay, because of this row. Let's write that as well. 0 equals B4. Okay. So when I see something like this, what I say to myself is the following. Well, I just translated this into system notation. But then, really, this says, oh, x5 is B3, given B. x2 is B2 minus this stuff. And x1 is B1 minus this stuff. And so when we're writing this system notation, what we would, when we're writing the solution set, what we would say is x3, x4 are free, right? x1 and x2 are completely determined once you figure out the values for x3 and x4. And you're free to choose whatever you want to choose for x3 and x4. Okay, makes sense? But where did these come from? This, the first column, corresponds to x1. Okay. This corresponds to x2 and so on. And so you see, whenever I was looking at a non-pivot column, in this case I have column 3 and column 4, when I was thinking about the solution set, turned into free variables. So the number of non-pivot columns is the same thing as the number of free variables. This is just the same way of saying, or different ways of saying the same thing. Does this kind of make sense? Okay. All right. So this is as far as I can go for now. Let's now switch over to figuring out the column space and the null space. Column space is the space of columns. Okay? So I just look at all columns, look at their span. Column space is a space of columns. Each column is 4-dimensional. So this column space is going to be a subspace of the output space. Span of this, 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 this. Okay, that's a column space. But there is some redundancy here, you see. This is perfectly OK to write. But the columns that correspond to non-pivots, so the non-pivot columns really are redundant. Okay? Because for instance, the third column I can write as a linear combo of the first two columns. Okay? And likewise, the fourth column I can write as a linear combo of the first two columns. So if I want, I could just get rid of the non-pivot columns and write it like so. What is the benefit of doing this? Because, well, it's rather straightforward to see that these three vectors are linearly independent, which means that these three columns, which ultimately are the pivot columns, constitute a basis for the column space. Okay? Is a basis of column space. Okay? How can I visualize this? Well, it's hard to visualize because these are 5 dimensions and 4 dimensions, but still we can try. Well, there are multiple ways of doing this. One method would be sort of using something like a heat map to describe sort of the values of certain components. But I don't really have access to many colors. So what I'm going to do is, for R5, I'm going to think of one 3-dimensional space and one 2-dimensional space. So this is R5. R4. Let's say these are x1, x2, x3, and then I have another axis, or two more axes, x4, x5. And then here I have two, let's say, two dimensionals. y1, y2, y3, y4. And so column space of A in this case then would be the span of, well, the first, so the everything in the y1 axis, everything in the y2 axis, the whole plane here, everything here, but also an extra dimension. So 2 dimensions here, 1 dimension here would give you the column space. Again, like I said, this is like a 4-dimensional thing, and how do you even visualize that? But you know, that's why we're doing linear algebra. Sometimes it is helpful to think about the shape of the column space. Sometimes it's not. What is important here is that ultimately, column space of A is a 3-dimensional subspace inside 4 dimensions. Okay? Any comments or questions about this? Okay. Now let's switch to the null space. Null space is by definition the collection of all solutions of Ax equals 0. So you see this time I'm going to look at this, but I'm going to fix B to be the 0 vector. So all of these are going to be 0. B4 is already 0. Well, I'll just delete it. 0. Okay. Well, let's reorganize things. And I can write it like so then. Ax equals 0 is the same thing as saying that x1 to x5 satisfy these things, x3, x4 free. Well, I can say it like so. X5 we know to be 0. Oh, I'll just start with this and then substitute. Instead of x1, I'm going to write this. 3x3 minus 5x4. Um, 5x4. x2 is minus 2x3 plus x4. I don't get to say anything about x3. I'm going to leave it as is. I don't get to say anything about x4. I'm going to leave it as is. And finally, x5 is 0. Okay. Well, I can then split this vector. I want to think of x3 and x4, these free variables, to be somewhat like something like scalars. And so I can write it like so. x5, 1, 0, 1, 0. Okay. Now what does this say? x3 and x4 are free, which means x solves Ax equals 0 if and only if it's in the span of these two 5-dimensional vectors. Okay? And so You can write it like so. Okay. Now again, these are 5-dimensional vectors. A goes from 5 dimensions to 4 dimensions. So this is a subspace of R5. Okay? Subspace of R5. Of the input space. Okay? I'm not going to even try to visualize this inside 5 dimensions, but it's fairly straightforward to see that these two are linearly independent because only the first vector allows you to move in the third direction, and only the second vector allows you to move in the fourth direction, which means that these are linearly independent, which means that these two vectors constitute the basis for the null space. Okay? And so for our purposes, when someone asks you to compute the column space or the null space, probably they're really asking for a basis. Typically, they would say, compute a basis for the null space, compute a basis for the column space. Yeah?
So we separated those from like the original column space because they were linearly dependent in the original span, right?
Which one are you asking? What are you asking?
These two, the null space.
Okay.
So we separated those because they were like linearly dependent in the original one, right?
Yes.
Okay. But then they're not.
Yeah, that's the confusing part. They sort of, so they do something like double duty. Like a lot of ideas in linear algebra do a lot of things simultaneously. Yes. Okay. Any other comments or questions? Now, I'm going to switch over to an example where the matrix is not row reduced to begin with, which means that you might encounter a matrix whose pivot columns are not that clear, which means that you're going to have to do some row reduction. But that row reduction procedure possibly is going to break null space and column space. Okay, so this is the complicated part. What it does preserve, though, is the number of vectors in bases. Okay? If you have a matrix like this, you get to compute its R number, its rank. Whatever that R number is, you're always going to have that many vectors in a basis for the column space. Okay? And whatever the number of non-pivot columns is, in this case 2, that's going to be the number of vectors in a basis for the null space. So you get to keep the number of basis vectors. But maybe the shapes are disturbed. Okay? So this is the idea behind dimension. It turns out that, forget about column space, null space, any vector space, at least for our purposes. So if I were to take, let's say, v1 dot 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 vp in V, also w1 dot 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 wq, let's say q is a different possibly number than p. If this is a basis and this is a basis, well, p has to equal to q. if these are two different bases, then the number of vectors in the first set has to equal to the number of vectors in the second set. P equals Q. And this common number, common integer, you call the dimension of V. Okay? And so when you read the textbook, for instance, the way they would define rank is, well, they would say rank is a dimension of the column space. Okay? I didn't do it that way. I fast-forwarded everything. Because by the end of week 1, you know how to compute reduced forms, which means that you know how to compute number of pivots. So we just like fast-forwarded that. But that's all there is to it. Okay? Rank is the dimension of the column space, and the other number is nullity, which is the dimension of the null space. Dimension of this is nullity, dimension of this is rank. Okay? We're going to keep working on this on Monday. Thank you.